Good day. Welcome to my hydropower engineering presentation focused on the Maguga Dam hydrology assessment. My name is Joanne Correa, student number 629-33590 from the University of South Africa. The Maguga Dam on the Komati River was completed in 2001. The project was a joint opportunity for both the Government of South Africa and Eswatini. The dam is managed by the Komati River Basin Authority. The full capacity level is 625 meters. This dam provides water for irrigation, domestic use, and hydropower generation. Given the significance of regional water management and energy supply, the managing authority now seeks to review the dam's efficiency and effectiveness, particularly during dry periods, as they have experienced plenty of late. The review will focus on three main areas, which are affirming water availability for hydropower, evaluating the adequacy of the civil works, and assessing the main electromechanical components of the dam. Using Google Earth Pro, I identified the hydropower plant components typically found in a run-of-river hydropower plant. To the left is the overflow. Should the dam reach full capacity, the water will naturally drain into the plunge pool. This plunge pool serves both as to regulate the water from the overflow as well as to have a water supply in case of emergencies in the power plant. Above the plunge pool is the transformer. This then uses the transmission lines that go upwards towards the road and feed into the grid. The water intake is to the north of the power plant in the dam. It is assumed that the water will enter the intake channel and then drop vertically down. The pipe will then slope underneath the dam wall towards the surge tank, and from there it will enter the powerhouse where the water can be converted into power. The additional water can then be released through the tailgate. For the penstock or conveyance channel length, I had one notable limitation of Google Earth Pro. This was the inability to accurately measure lengths of paths drawn in due to the line drawn following the natural terrain level. This limitation necessitated an estimation approach for the penstock length. This estimation may prove some uncertainties, so should the project proceed, more field measurements are required or advanced remote sensing techniques to be precise of the underground components. Using the scale bar, I scaled the image and aligned the bar to be parallel to the drawn-in pipe to estimate the approximate length of the pipe from the intake to the surge tank. This was then estimated at 310 meters long. This did not include the additional pipe that would be vertical from the intake structure to the bottom of the conveyance channel. The total inflow per year was provided from the year 1920 to 2009. This was converted to an average daily inflow per year, taking into account years that would have an additional day due to it being a leap year. Ranking the daily inflows in descending order from 1 to 90, whereby 1 was the highest daily inflow and 90 was the smallest, meaning at 90, this was the driest period. The probability of exceedance was calculated for each rank inflow. This probability indicates the likelihood that a given flow rate will be equaled or exceeded. After the flow duration curve was plotted using the exceedance calculated, we could then get the 90, 95, 96, 98, and 99% exceedances, which we could read off the graph or use the tables. We convert this from million cubic meters per day to cubic meters per second. This could then be used to calculate the firm discharge, which is then used for later calculations. For the 90% exceedance, we got 9.515 cubic meters per second. For 95, we got 5.993 cubic meters per second. For 96% exceedance, we got 5.231 cubic meters per second. At 98, we got 3.839 meters cubed per second. And at 99%, we got 3.829 cubic meters per second. Using QGIS, I imported the shape files to provided to me to create layers in the program. These layers can be edited to get the best display for generating maps. To generate a map, you would select File, New Print Layout, which will open a new window whereby you can import the previous map from the project workspace. This will allow you then to add labels, legends, and scales to produce report quality maps. In the project window, we can extract the areas from the Maguga Dam topo-poly layer by right-clicking and selecting Attribute Table. The results for the area display as kilometers squared, but can also be changed to add a column to cover the information for meters squared. This is done by editing the ID information and requesting the $area function, which uses the SI unit that the layer is currently created on. This information can then be copied onto the clipboard and imported to another program. Okay, displayed you can see the two maps produced, namely the Maguga Dam intake level and full supply level map, as well as the dam catchment area map. Importing the data received from the attribute table from QGIS, I will then need to filter this information as various elevations had multiple values. To do this, you would sum up the areas for each elevation to ensure that it's one entry per elevation. Once this is complete, you can then use that to calculate the storage. I use the trapezoidal rule method, whereby you take the area of a contour plus the area of the next higher contour and divide by 2. You multiply this value with the elevation of the higher contour minus the elevation of the lower contour. This will then give you the storage for that specific elevation. This was completed for each item and each elevation. After that, you could complete 2 graphs that can be plotted, an elevation versus area graph and an elevation versus storage graph. It was noted in the project brief that the intake level was 550 meters and the full supply level was at 625 meters. This was confirmed in QGIS under the layers property for both of those mentioned layers. To calculate the full supply capacity, I took the area in meters squared for the full supply and divided by 2. I used the initial area as 0. This is then multiplied with the difference between the full supply level and the intake level to get a full storage capacity of 332 million cubic meters. Next was to calculate the head gross and the drawdown. For head gross, I assumed the intake as the lowest water level. Therefore, it is high water level minus low water level to get 75 meters. For the drawdown, I first needed to calculate the normal water level, which was calculated as 600 meters. Then, assuming the tail water level as 526 meters, I got that from Google Earth as placing the cursor over the tail water level. You could read that it was 526 meters. From there, you could calculate the drawdown as 74 meters. To determine the impact the storage has on the firm discharge, I first converted the given demand from million cubic meters per year to the million cubic meters per day. I used the given water demand strategy table to calculate the demand at each exceedance. Once I've done this for domestic water demand, irrigation, hydropower, and ecology, I added them all together to get the total exceedance and compare this with the existing storage capacity calculated. It is evident that at no exceedance probability does the available water meet the total daily demand for all the sectors. This indicates that the water availability at the Maguga Dam is insufficient to meet the cumulative demand for domestic use, irrigation, hydropower generation, and ecological needs during the driest periods. To calculate the power generation, I assumed efficiency as 95%. The gross head was calculated at 75 meters. The density of the water is standard at 1,000 kilograms meters cubed, and gravitational acceleration is 9.81 meters cubed per second. The calculated firm discharge was then used. For power at 90% exceedance, we obtained 6.651 megawatts. At 95% exceedance, we get 4.133 megawatts, and at 98%, it produces 2.648 megawatts of power. This review of the Maguga Dam underscores its essential role in regional water supply and energy supply, especially during these recent dry periods. Through the use of Google Earth and QGIS, the study effectively mapped the hydropower plant components, analyzed the flow rates, and assessed the dam's physical characteristics and storage capacity. The results indicate that the current water availability at various exceedance probabilities is insufficient to meet the total demand across all sectors, highlighting the urgency for robust water management strategies. The potential for hydropower generation is significant, though it is constrained during dry periods. This emphasizes that the need for enhancing the dam's storage capacity and integrating advanced technologies to improve efficiency. By adopting predictive models and climate adaptation measures, the Maguga Dam can better manage the variability in water inflows and sustain its performance. The project affirms the necessity of continuous optimization of the dam's operation. Implementing sustainable practices and efficient electromechanical components will not only bolster regional energy needs, but also contribute to sustainable development and climate resilience. For future efforts, we should focus on collaborative water management approaches and technological innovations to ensure the long-term sustainability and effectiveness of this Maguga Dam.